I think today we will finish chapter 7, and next week I'm going to cover chapter 8, and the week after next will be the final week, the final exam. Question? Any questions so far for chapter 6? If not, then let's move into chapter 7, Internet QoS. Okay, so we have finished up from chapter 1 to chapter 6. We have finished the protocol layers, all the protocol layer issues, all the protocols. But there are two advanced topics that we haven't covered. One is QoS, one is security. So chapter 7 and chapter 8 will cover these two. And why these two are important? Because on the internet we want the internet to be fast, okay, and we want the internet to be secure, to be safe. And I would say having a fast internet is a never-ending story. Where because if the application pump more traffic than the network can carry, then you have congestion. Then you will say that you need QoS. But if you invest a lot of fiber optics, a lot of technology, wireless technology or wire technology, to increase the bandwidth of the network, then it would not become a problem. The QoS would not become a problem. But when that happened, people would develop newer applications that would pump even higher traffic. Then you got congestion again. In that case, then QoS become a problem, a concern. So you see what happened is before 2000, the year 2000, QoS is a big issue because everyone feels internet is too slow, and we often need to wait for, I believe, it's often that we need to wait for 10 seconds or 7 seconds for the web page to come out. Okay, it was 1993 when web www was developed. And then later on, around late 90s, we suffer a lot of congestion. The bandwidth is too limited, and a lot of traffic, a lot of web traffic. So so QoS was a big concern at that time, and a lot of research work, a lot of solution developed. We would look at some of the most of the solution in this chapter. But then around the year 2000, together with the internet bubble, a lot of investment on fiber optics. Okay, so we probably only see around the year 2000, we only see the bubble caused by website, right? But website is the major bubble. But there are other bubbles, which are fiber optics. Even the railroad, the train company, are investing on fiber optics in many continents. So they have fiber optic, invest a lot of fiber optics, and that changed the scenario. That increased the backbone from the backbone of the internet from hundreds of megabit per second to gigabit or 10 gigabit per second. So the backbone of the internet has been the bandwidth has been increased by 1 or 2 order of magnitude. So after that investment around 2000, say 2003, the QoS is not a concern. Not a big concern then, because a lot of investment in the backbone. So, but then again, people start to develop new applications. For example, what are the new applications that will consume a lot of bandwidth? The one is big P2P, one is streaming. And I believe that one day if we have high definition HD streaming on the internet, the bandwidth will be a problem. Right now, what we see on YouTube is what? Is not even standard resolution, but low resolution. If you consider your TV, your TV, say your digital TV as the standard definition, the YouTube is not standard; it's a low definition. Okay, but even if you want to change the content on YouTube to the standard definition, then the bandwidth requirement will increase by one order of magnitude, one order. And if you want to change from standard definition to high definition, that might be another order magnitude of upgrade in the bandwidth requirement. So the web was an early contributor, but web is not a major consumer of bandwidth right now. But P2P is. Voice over IP is not a big concern because the voice traffic is low compared to video or compared to P2P file. So voice over IP is not a big consumer. But video is teleconferencing with video, and it contributes more than voice over IP. Streaming is a contributor, but not as significant compared to P2P. But so right now it's a racing between P2P application and video streaming. And then before the video streaming is standard definition or high definition, P2P will take the lead. But if the video streaming becomes standard definition and high definition, it would increase. It would surpass. It would surpass the P2P traffic. Okay. So it's the concern of QoS is oscillate through the years. It was a concern before 2000. It was less concern before 2008, and later on, when P2P traffic and streaming traffic increases, especially when we are talking about IPTV, meaning TV quality over internet. Right now, we don't have much application with TV quality on the internet. Mostly just a low resolution video. But if we have real IPTV with a standard definition or high definition, then QoS will become a concern again. So I expect that in somewhere in this decade, it will be a concern. Okay, so we look at the general issues. If we want to impose QoS on the internet, what should we do at a control plane and also at the data plane? And we can see 6 issues to consider. The first 3 are control plane issues, while the remaining 3 are the data plane issues. Before the year 2000, there were 2 solutions. Around the year 2000, there are two solutions. One is integrated service, one is differentiated service. They are both total solution for QoS. And in fact, there are architectures, QoS architectures, that they expect to impose on the internet. Okay, either globally or ISP wide. Okay, but they failed. Both of them failed. And the reason why they fail is because the major reason is because statefulness. Those two mechanisms will turn the routers, the backbone routers, into stateful. However, we say that IP routers are what? Stateless. They are stateless. They don't keep the state information for the flows passing by. For the flow passing by, I just treat them as an IP packet individually. I might be carrying 1 million packets per second, but I treat each one of them independently. I don't try to recognize them to see how many flows are passing by, how many TCP connections, how many UDP connections are passing by. I don't treat them as a group of connection or flows. I don't. I treat them independently as packets. 1 million packets. Okay. So that's a status of the router. Statelessness of the router. But these two architecture, they try to turn a router into stateful. And to do that, the change is too big, and it almost destroyed the original essence of the original design. So they failed. We'll look at more detail on why they failed and how they plan to do it, and how different these two architectures are. They differ from each other, where the integrated service is a fine granularity. They try to provide QoS to every flow. However, the differentiated service try to provide QoS to every class, and a class could have multiple flows, could have many flows, and there are only a limited number of classes. Okay, so the difference is per flow versus per class. And under these two architecture, these two are only architecture for QoS, but they need to be QoS components. And there are 6 algorithms. I mean, for those 6, you need 6 kind of algorithm to do the job of a QoS component. Okay. So now what? These two architecture failed, and are we using any of these QoS components now? The answer is yes, partially. You don't use much on this in today's product. In today's networking product, you use some of this, but not all of them. But for example, for this one, you don't use it mostly. For this one, yes, you use them to classify packets. Yes. And for this, yes, you use it. You use to limit. You use it to limit the rate, data rate. For example, some switch now provide the rate limit feature. Rate limit feature means that okay, I give you a gigabit port. However, you couldn't pump a gigabit all the time. If you pump gigabit all the time by this single PC, you pump all the time, then my backbone will have a problem. So I might limit the average bit rate of this port to say 100 megabit per second. Even though this is a gigabit interface, 1 gigabit interface, and when you transmit at a 1 gigabit speed, but the average bit rate will be limited to 100 megabit per second. That's the average. It's like when you pump, you can pump gigabit, but you can't pump all the time. You can only use 1/10 of your time to pump. 1/10 of your time of the time duration you can pump a gigabit. You can pump 100%. 10% of your time you can pump a gigabit, but not all the time. So that's a rate limit feature that has been implemented in most advanced switch. Most advanced layer 2 or layer 3 switches, they implement the feature of rate limit. And that rate limit needs to be implemented with the mechanism similar to token bucket. We'll look at that next. And for packet scheduling, yes, they are doing that, especially in the router that needs to divide the bandwidth into different applications. For example, in Cisco's products called P-Cube, which is a product that can recognize P2P applications, and then try to allocate bandwidth for certain category of P2P application. For example, in Cisco P-Cube, they can allocate bandwidth to P2P. Well, they limit the bandwidth for P2P, and also give allocate bandwidth to voice over IP, say SIP traffic. Okay, and they can allocate bandwidth to the other, say, web application. For if they need the web traffic to be fast, then they could allocate the bandwidth. Then that kind of allocation, I have allocated bandwidth to several classes. Then how do I enforce the allocation? How do I enforce the bandwidth allocation? That's by packet scheduling. You need to schedule the packet. Schedule the packet among different queues. 1 queue per class. So that is used, but not in many products, but in some products. This is probably more popular, implemented in many switches, but this is implemented in some high-end product with bandwidth management features. How about this packet discarding? Yes, it is used. It is used in a backbone router. The packet discarding mechanism is the most representative one is called RAID, random early discard. Random early discard. It's a queue, but it's not FIFO. It's not first in, first out. In the traditional FIFO, what you do is that if the queue is not full and the packet comes in, then it will be queued, right? Until the queue is full, then the next packet comes will be dropped. That's FIFO. But RAID says that it's not good. The FIFO is doing a tail dropping, which is not good. Because when it's full, when you have a burst of packet coming in, but the queue is full, then all packet in the burst will be dropped. So you would have consecutive drops, which is not good to some application. For example, if I suffer 10% or 20% packet loss, I can recover my video content. If I do layered coding, or if I do redundancy coding on my video content, right? And another thing that will be bad is if multiple TCP connections are passing through the common bottleneck, meaning that they are competing, that they are passing through the same queue. And you have tail dropping, so all of the packet will be dropped. All of the TCP packet will be dropped. And when they are packet dropped, then all of the TCP source will do what? They would have a triple duplicate egg, or they would time out, either one. And they will do what? They will shrink the window size. So they will do a congestion control simultaneously. So they will slow down simultaneously, and then the congestion will be relieved. And then they will detect, okay, the congestion is relieved, and I can send. I can increase my window size. So they would synchronously decrease the window size and increase the window size. And when they increase the window size, they will what? Congest again. So tail dropping is not good for these two scenario. One is a so-called synchronized TCP congestion. TCP synchronized congestion. Another scenario is for multimedia traffic with a layered or redundant coding. So we don't want tail dropping. So how should we do? We would do what? When a packet comes and the queue is 80% full, then there will be a probability that this packet will be dropped. So even though the queue is not full, this incoming packet might be dropped. And when the queue is 90% full, a packet arrive would have an even higher dropping probability. Okay, so the queue is 60% full. I might start have a dropping probability that is non-zero dropping probability. But when the queue is 80% or 90% full, the dropping probability will be higher. Okay, so for example, when it's 60% full, the dropping probability is 0.3. When it's 70% full, then it becomes 0.5. 80% full, then become 0.6. Okay, then you would arrive. The arriving packet will be dropped with the probability, and that probability depends on the queue occupancy. I mean the queue length. Okay. Then in a sense that you would have a random dropping instead of a consecutive dropping. Okay. So the dropping will be randomized, and won't be consecutive. You won't have consecutive. I send 100 packets, and 100 packets are dropped. No, it won't happen. It would probably, among the 100 packets, 30% of them are dropped. But I still managed to have 70 packets pass through successfully. And for many applications, having 70% packet arriving the destination will be okay, because the video might be recovered to some degree. Okay, so that's that red packet dropping, the red RED, randomly discard, is actually implemented in the core routers. But these are actually, I would say in most core routers, they implement red. Okay. So in a sense that we don't, the umbrella architecture, integrated service and differentiated service, the architectures are not successful, but the component, the algorithm, the mechanism developed over the year have been deployed in existing products, and they help the QoS to some degree. I would say that they are partial solutions, but not total solutions. It's like you wouldn't have a perfect marriage. Okay, that never you never had dispute with your wife, but your marriage has been embedded some mechanisms to reduce the conflict. So the marriage is still stable, even though you don't have a total solution to avoid any conflict. You still have conflict, but the conflict won't be too serious. So at the end, you are not getting a perfect solution. These two, perhaps with these two, you got a perfect solution, which is total solution. But you don't have the total solution. You put just the partial solution. So it won't be too bad. And so that's the reality. Okay, so I kind of summarize what we want to cover in this chapter. And let us take a 10 minutes break. So let's look at the problem we had. There's no QoS quality of service. There's no guarantee of the quality on the internet, and only the best effort. Only best effort has been provided. Best effort, again, best effort is not best. It's they try the best. They try their best to deliver the packets, but no guarantee. But the internet architecture is so popular that many applications hope to get some kind of guarantee on the quality, either in terms of the bounded delay. The delay should be bounded. I send a packet and the delay should be bounded, or guarantee the rate, sending rate. Okay, can you provide me a guaranteed bandwidth of 3 megabit per second? 3 megabit per second guaranteed. Okay. However, the internet cannot provide that. Cannot provide a guarantee on the delay or latency, and cannot provide a guarantee on the sending rate. Okay, so so then can we have an architecture, internet architecture, that would guarantee QoS? The answer is yes, it's possible. So the society come up with two total solutions. One is integrated service. The other is a differentiated service. The difference between these two are one is per floor. They try integrated service, try to guarantee the QoS to each floor on a per floor base, while the differentiated service try to provide a guarantee on a per class base, per class. And why do we come up with the two solutions? One, because the integrated service is too detailed, too complicated, too scale, too complicated to scale. So we reduce the complexity from per floor to per class, and the number of floor might be thousands or tens of thousands, but the number of class might be just below 10 or 10. So then you can group the floors into just a small number of classes. Group the floors into a small number of classes and provide the QoS to these classes. Okay, these are the goal, but it failed. Still today we still don't have the guarantee. The internet is still best effort. No guarantee on sending rate, no guarantee on delay, latency. But as long as the best effort is good enough, then it would not be a big problem. As long as the the best effort. And whether the best effort is good enough is really depends on the bandwidth, how abundant the bandwidth is. If the internet infrastructure has abundant bandwidth, then you don't need to impose much control, like either the total solution or the partial solution. You don't. But the bandwidth is not abundant in the infrastructure, then you need to provide either partial or total solution. Right now, the backbone is less likely to be the bottleneck. But where is the bottleneck? The bottleneck has been shifted to the edge of the network and also to the servers. The server, when you access something, it's slow. It might be the network. It might be the server. So you need to know whether it's the server. The server is heavily loaded. Then the content you want to retrieve will take a long time to get back. So it might be the server, it might be the network. Recently, it shifted from backbone network to servers, and also to the edge of the network. So the research has been on a lot on servers. How can we provide better quality of service by readjusting the server architecture, or have server clusters. Okay, so and also the edge of the network. On the edge of the network, we have what? We have Ethernet. It's not a problem. The Ethernet bandwidth is abundant. We have what? Wireless LAN. It is a problem. Wireless LAN is a problem. The bandwidth is not that good when you have many obstacles indoor. Okay, or you have many people competing the bandwidth of the wireless LAN. After reading chapter 3, you should have known the problem of CSMA/CA with RTS CTS, right? It's a still a contention-based protocol with RTS CTS to reduce the chance of collision. And even though we have advanced to 11N with much more bandwidth, but in the field test, in the lab test, the bandwidth could be 100, 100, 200 megabit per second. But in the field, it's often that the bandwidth drops to tens of megabit per second instead of hundreds of megabit per second. So the bandwidth is still not as abundant as Ethernet. On Ethernet, for the desktop, you have 100 megabit per second or even gigabit per second. But on wireless LAN, it's several tens of megabit per second shared by many people. Okay. So wireless LAN is a little bit problem. How about you are out of the wireless LAN coverage? You are out of the Wi-Fi coverage outdoor or traveling. Then you need to rely on 3G. 3G, right? I think most of you are using 3G data service, right? You pay like 700 NT dollars, like 25 US dollars to get a freight rate, monthly freight rate. But what is your experience about 3G? Terrible, right? Bandwidth compared to Wi-Fi, it's terrible. And Wi-Fi is not as good as Ethernet. So Ethernet is perfect, but Wi-Fi is okay, but not very good. But 3G is terrible. And so that is a problem. So the age of the router, age of the network, and also ADSL. Right now, ADSL we got I think I got 10 megabit per second or something like that at home. But 10 megabit per second is one order less compared to my 100 megabit per second Ethernet. So so DSL is still not as fast. Okay, so DSL is slightly a problem. Wi-Fi is slightly a problem, but 3G cellular, the wide area or metropolitan area wireless is a problem. Is a big problem now still. But we would migrate to LTE, the 4G network, probably in 2 or 3 years, maybe 5 years. Within 5 years, we will migrate to LTE. That will give you a megabit per second throughput. Okay, so that will be alleviated later on.